Before we move on to other functions, let's also take the partial derivative of our function here, f of x, y, or the partial derivative of z with respect to y. So I'll do it in magenta. So the partial derivative of z with respect to y. Well, now we're saying how much does z change with respect to y if x is constant. So this x squared, we treat it as a constant now. So the derivative of a constant with respect to y is 0, so you ignore it. Now, this xy term, the way we're viewing it now is y is the variable, x is the constant. So what is the derivative of, I don't know, 5y with respect to y? Well, it's 5. So the derivative of xy with respect to y is just x. And what's the derivative of y squared with respect to y? Well, it's just 2y. So as you can see, it's quite symmetric. The partial of z with respect to x is 2x plus y. The partial of z with respect to y is x plus 2y. And that's because this equation is pretty symmetric. The x's and the y's kind of do the same thing. Now, we picked the point x is equal to 0.2, y is equal to 0.3. Actually, let me erase this, because I picked a different point where I graphed, and I graphed it ahead of time just to save time. So I don't think I have to include this anymore. So what I did is I picked the point x is equal to 0.3, y is equal to 0.3. And when x is equal to 0.3, y is equal to 0.3, what is z equal to? So you have 0.3 squared is 0.09, 0.3 times 0.3, 0.09, 0.3. So it's z is equal to 0.27, right? Just substitute 0.3 in for x and y. Z is equal to 0.27. So what is the partial of z with respect to x at that point? Or we could write f sub x at the point y. X is equal to 0.3, y is equal to 0.3. It equals, we figured that, let's see, 2 times 0.3 is 0.6 plus 0.3. That's equal to 0.9. So the slope in the x direction at that point is 0.9. And then if we take the partial with respect to y at that same point, 0.3 plus 0.6, that's also equal to 0.9. So let's see if we can visualize this. So let me bring in my graph. There we go. So this surface, once again, is the surface of z is equal to x squared plus xy plus y squared. And this box is kind of the domain and the x and y dimensions that I defined. I bounded it because it starts to increase really fast, and then you wouldn't be able to see all of this interesting stuff that happens closer in. But what I did, so this vertical line, I just wanted to show you that when x is equal to 0.3, y is equal to 0.3, z is equal to 0.7. So that just kind of shows you that, okay, that shows what point we're working with. And then these two lines, this is, if you think about it, this is a line where y is constant, right? So this is the slope as z, or as the surface changes with respect to x at this point, right? So this is the tangent line relative to x, or you could kind of view it as, if you hold y constant, here's the tangent line at that point. And then if you hold x constant, here's the tangent line at that point. And like I said in the last video, you could actually have an infinite tangent lines. You have to pick the direction that you want to go in the xy plane, and then you could plot a tangent line. And so that's why we did partial derivatives to begin with. And actually, this is pretty cool. We can actually take, let me get my mouse. We can actually zoom in on this. Zoom in a little bit more. Actually, I want to zoom in on the part that is interesting. Let me translate this. So that's the part that's interesting. And now let me rotate it. So you can actually rotate. So this is the tangent. This shows that the partial of the function with respect to y, the slope is 0.9. And this line shows that the partial of the slope, or the partial of the function, the partial of z, or the partial of the function with respect to x, is 0.9 at this point. At the point x is 0.3, y is 0.3, right? X is 0.3, y is 0.3, z is equal to 0.27. And we can rotate it just to get more intuition. And I think it's the graphing thing looks a little bit funny sometimes, but you see that both of those lines are tangent at that point. And in fact, two lines define a plane, and the plane that's defined by those two lines, or any of the two tangent lines to that point, defines a tangent plane to this surface. So a surface does have only one tangent plane, but within a tangent plane, there are an infinite number of tangent lines. Well, anyway, that's the fun with graphing. Now let's just chug through a bunch of partial derivative problems just so that you get used to the mathematics of it. So delete that. Let's do some that might confuse you, just so you see how to do them. Let's say that f of x, y, and I'm confining it to 3 dimensions, although we can do it more. Actually, maybe I'll do it in more dimensions now. We're not going to try to visualize it. Let's say it's x sine of x cosine of y. Aha. So let's take the partial of f with respect to x. And this is still going to be a function of x and y. So we treat y like a constant. So if cosine of a constant, this is just going to be a constant. So we can almost ignore that. We could put that out front. We could say that it's going to be cosine of y times the derivative of this with respect to x. So you could say cosine of y. It's just a number. It could be, this cosine of y could just be, I don't know, 5 or pi or whatever. Cosine of y, and then, because when you take the derivative, the constant just comes out of the derivative. And then we can take the derivative of the x's. So the derivative of the first term with respect to x, well, that's just 1 times the second expression, so it's sine of x. I'm just doing the product rule here. Plus the derivative of the second expression, that's cosine of x. Cosine of x. Cosine of x is the derivative of the second expression times the first expression times x. So if we wanted to expand it all out, the partial of f with respect to x, it's a function of x and y, it equals sine of x cosine of y plus, let's put this x out front just so change the order, x cosine of x cosine of y. Not too difficult. You just have to realize that anything with the y is a constant. So let's reverse it. Well, not reverse it. Let's take the partial now in the y direction. How much does f change in the y direction if we hold x constant? So the partial of f with respect to y, still a function of x and y. The derivative in that direction is a function of f and x and y. So now x is a constant. So this actually becomes pretty straightforward. This whole x sine of x, if x is some number, 5, this is just a constant. So we can just write that out front. So that's just x sine of x. It's just I know it's hard for you to get used to saying that, oh, x sine of x, that's just a constant number, because you're so used to taking the derivative with respect to x. And that's the hardest part about doing these partial derivatives. But anyway, this is just a constant term, and now we just take the derivative of this with respect to y. The derivative of cosine of y with respect to y is minus sine of y. So I'll do that in yellow. Minus sine of y. I just wanted to put the minus out front. Minus sine of y. There you have it. Let's do another one. And actually, I'm going to add more variables. Just to let's say that, I don't know, just so you get used to the different notation. X is equal to a squared times, I don't know, a squared times b to the third times c to the 1/2 power. Now, what is the partial derivative of x with respect to a? Well, everything else is just a constant. What's the partial of a squared with respect to a? Well, it's 2a, so it'll just be 2a times the constants, times b to the third, c to the 1/2. I could actually get rid of my parentheses there. What's the partial derivative with respect to b? Oh, sorry. What's the partial of x with respect to b? Well, now a squared and c to the 1/2 are just constants. We could just write that. A squared c to the 1/2. And now we just take the derivative with respect to b. Well, that's 3b squared times 3b squared. And if I just want to rearrange it, that's 3a squared b squared c to the 1/2 power. Not too difficult. You just have to keep in mind what's constant and what's not. And then finally, the partial of x with respect to c. A squared b to the third, those are both constants. A squared b to the third times the derivative of this with respect to c, 1/2 c to the minus 1/2. Or we could rewrite this as what? A squared b to the third over 2 square roots of c. Just a little bit of algebraic manipulation. Anyway, I will see you in the next video.